Okay, so good day everyone. Let's continue our discussion on random access MAC protocol. So we're looking at specifically the MAC protocol that are designed under the random access schemes, right? So last class we understood pure Aloha, and we also understood the refined version of pure Aloha, which is your slotted Aloha. And we understood that slotted Aloha gives improved performance and efficiency of maximizing the throughput compared to pure Aloha. But please understand, both are really bad because collisions are still there, right? There's a higher chances of collision because you're not having much rules here. You have data frame to send in pure Aloha, it just like that send. And so there's a higher probability of collision. And the maximum throughput that we can achieve using the model that we had, right, is basically 18%. Whereas slotted Aloha, they brought in a time slot strategy. And if you have frames to send, you wait till the beginning of the next time slot if you miss the time slot, and then you transmit. But still, that vulnerable time was during your frame transmission time where there is a probability of collision. Multiple stations can transmit during the beginning of the next time slot. You can't avoid that, right? So that was the drawback that we had in Aloha scheme. So today we will go on and look at much more refined designs, right? And we will start up with understanding CSMA. So if you can recall CSMA, CSMA stands for Carrier Sense Multiple Access Scheme. So this was an idea that became very popular and was started used in different standards, right? So Carrier Sense Multiple Access, we will understand that first. And then we will understand two standardized protocols, carrier sense multiple access / CD. So it is augmented with another feature called collision detection. And this was adopted in Ethernet in the early days. So the standard IEEE standard is called as IEEE 802.3. And the first version of Ethernet that came in was standard Ethernet. So those days you only had bus topology and all these devices were Ethernet enabled, right? Capable of transmitting up to 10 Mbps. So that was the first evolution of Ethernet that came in. So here, the standard that was adopted by the devices MAC protocol was adopted was CSMA CD. CD stands for collision detection. So the devices has the capability to detect whether collision has happened when I'm transmitting a frame. That was brought in CSMA CD, right? But then Ethernet has evolved through several evolutions, right? Now we are in a world called gigabit Ethernet, where we are transmitting at a rate of 1 Gbps, right? And we have completely moved to a full duplex Ethernet, standard, where simultaneously you can transmit and receive over a dedicated link, and star topology has outbeaten, all that, right? So in between gigabit, the earlier one was fast Ethernet, which is 100 Mbps, right? So I think, yeah, we have gone through a very big evolution in the Ethernet standard. But what we are now looking at is first on the MAC aspect of it. But please understand this 802.3 standard Ethernet is the first LAN, widely used LAN over those days, right? LAN standard, and CSMA CD was used over the multi-point link. And then CSMA CA, which was parallelly the wireless dominated. So IEEE, the Wi-Fi standard came in, right? So IEEE 802.11, which is your Wi-Fi standard, at the MAC adopted this CSMA CA scheme, which means the CA stands for collision avoidance. Okay, so we will discuss on first how CSMA works, and then we will later get on to how CSMA CD works, right? And then later we'll get on to the wireless, standard WLAN, wireless LAN standard, which is where we'll focus on the MAC aspect of it, which is CSMA CA scheme. So that's going to be the discussion for our lecture, first half of this lecture today. Okay, so let's get on first and understand CSMA, right? Why was this protocol proposed? That's the first question that we have to do. Ideally, you know that random access protocols, any station has frame to send, right? Has the right to send. But since it's a common shared medium, there is a higher probability of collision, and that is what we have to minimize. So ultimately, our goal here is to minimize the chance of collision that's happening, thereby increase the performance. That is what we want. Pure Aloha, slotted Aloha was the first few schemes that came in, but it suffered from a higher probability of collision. We want to further reduce the probability of collision that's happening, and that's where this idea came in. So the idea here is basically to reduce the chance of collision. How can you reduce the chance of the collision here is we want to bring in this scheme where before you start talking, you listen if someone is talking. Right. So this is what I was trying to explain. So you listen before you talk. Unlike the other schemes where you're just talking, here you're going to listen if someone else is talking. If someone else is talking, you should wait till they stop, right? And then try talking, right? So that is the idea. So this is a conventional idea. Let's now technically understand how it's applied in CSMA. In CSMA, what we're going to bring in here is we are actually going to sense the medium. Every device that has a frame to send or transmit or multiple frames to transmit will first sense the channel, sense the medium, right? So if the medium is, so we basically look at the state of the medium. So what do you mean by the state of the medium? What will this state return? Is depending upon the state of the medium, you can return whether the medium is idle or the medium is busy. So how would you go on to perform this, sensing and going on to return back the state of the medium is the device is going to do a process called energy detection, right? So what do you mean by energy detection is if you go on to listen in the medium, you go on to sense the medium, right? You're basically detecting the presence of signal energy. If the signal energy is detected, then you will go on to return the state of the medium as busy. Someone is using the medium. If the signal energy detection is minimal or it's not there, right? Then you go on to return the status as idle. So these are the two states of the medium that is being returned by the device that uses the sensing capability to sense the state of the medium. So you perform this energy detection at a carrier frequency. Why it is called as carrier sense multiple access? The word carrier is generally used to carry your information, right? So if you want to travel faster, you know that we will travel either in a flight or in a train, right? So that's a very fast carrier, right? So here when we talk about in wire or wireless, we talk something in terms of a frequency that we use, the carrier frequency that we use to carry the information signal, right? Whether you're going to use a high frequency carrier and all that depends upon what standard you're working on. So the carrier frequency, where is your information being carried? So these devices perform the energy detection at the carrier frequency, right? And then they go on to return the state of the medium, whether the medium is busy or idle based on whatever energy is detected in that, right? So that's what we call as sense before transmit. So CSMA scheme is sensing the medium before they start transmitting, right? So this is an additional feature that has been brought in to further reduce the chance of collision. We are only further reducing the chance of collision, and we are not completely avoiding collision. Because when multiple guys wanted to talk, right, they both are listening, right? And if someone, then they see the medium is idle, they immediately start talking, right? That could also be a problem, right? So it takes some minimal amount of time for you to before you sense and make a decision, right? Someone, if would have captured the medium, that could also result in a probability of collision happen, right? So what is that vulnerable time in CSMA? Unlike when you compared with your slotted aloha and pure aloha, right? Where when you are talking and someone is talking during the time that you're talking, we had a collision, right? Here we are going to sense before we start talking. But here again, there is a minimal time where there could be a probability of collision. So that we will try to understand here by looking at how we can model this. Okay, so this is CSMA for you. So looking at this picture, I think we can further try to continue our discussion. So I'm going to use a concept here where when do you think collision will still happen, where CSMA will suffer in terms of collisions, right? So stations which are using CSMA will suffer collision. So the first point that we have to understand here is we'll look at that. This is a bus topology. There are multiple stations that are tied over the bus, multi-point link, right? And these stations are separated by a distance. So we'll say that x-axis is like your space, right? And y-axis is your time. Okay, so the vertical scale is shown as a time because signal has to propagate, right, over the bus. So I'm going to use a model called the space-time model to explain how the signal propagates over the medium, and where we could still go on to say that the medium is idle and collision happening. So this we have to analyze. And so the model that I'm going to use is called a space-time model. Signal is propagated over the space, and over time you are transmitting your frames, which will take some time to transmit. Multiple devices over the LAN is going to transmit. So imagine this bus as a pipe, okay, pipe where water is going to flow, right? So I think we will understand this because when every devices are trying to sense the medium, now they have the capability to sense the medium, right? So when a device is sensing the medium, and he will return the state to be idle if the medium is free. But just imagine when you're opening water in a tap and the water is flowing, the water takes some time to travel and fill the pipe. So imagine like a way where the signal is transmitted, right? And the signal to propagate over the medium and reach out, the bits to reach out to the other end will take some minimal time, and that time is going to be your propagation delay. Signal to propagate, right? And so before the signal propagates, if someone is trying to sense the medium and they find the medium state is still idle because the water has not reached, the first bit has not reached there, then he could go on to detect that medium is idle and start transmitting. Already water is coming, and so the collisions can happen. So that's why I want you to understand from this picture. We will clearly understand in the next slide where there is still a probability of collision happening because the signal has to propagate and fill the pipe, fill the case for the signal energy to be detected. So during that time, if someone is trying to listen, right, and capture the medium because the medium is idle at that point, right, he could still miss out, and there could be a probability of collision, right? Though it is very much going to be reduced, but the vulnerable time where there could still collision can happen is going to be the propagation delay, the propagation time for the signal to propagate. So we will understand that in the coming slides. So we will look at much more from a good 2D perspective, right, of how the signal is actually filling the medium, right? So this is called a space-time model, which is used to model how the collision can happen. So there are 4 stations, A, B, C, and D, tied onto the bus. Okay, so this is a common medium, right? Please understand this. It's a common medium, a bus medium. And so now the vertical scale, is your time axis, and your, X horizontal is your space where your signal travels. Now look at this. Now at time T1, right, the station B is trying to sense the medium. Okay, and the medium is reported as idle because no one is using it, right? Now, so the blue color one, so he starts to transmit the first bit. He starts to transmit at time T1, and the frame takes some, it's going to have a big length, right? That entire frame has to be transmitted. So multiple bits have to be transmitted, right? So which means you're going to fill it over the time. So the blue, shade that you see is the frame that is being transmitted by the station B. So at time T1, he transmits the first bit. It takes some time. So it's going to travel over the left and the right. It takes some time to reach on the either ends. And the max time that it could take to reach is going to be a propagation delay. Now, before the first bit reaches, right, to the point where the C is sensing, at time T2, C wants to transmit its data, right? So at time T2, which is slightly greater than T1, where the first bit has not reached out to that end, before that itself he's sensing the medium, he finds the medium to be idle, and he starts transmitting. And so the yellow portion that you see here is basically, the C frame that has been in transit. And so when the signal now goes on, right, over the medium, they collide and the frames are getting destroyed. And this collided signal will propagate, right, and reach the other end. And then they will understand that, okay, there is some collision happening. So this is the problem. So when we look at from the space-time model, for the signal to propagate and reach to the, dead end of the medium, so that others, when they sense it, will see that the medium signal energy is present, will take some minimal amount of time. And that minimal amount of time where you could miss out and there could be a probability of collision is your propagation delay, or the propagation time. So the vulnerable time for CSMA scheme is the maximum propagation time. Why I'm saying it as a maximum propagation time is, say A and D are the stations which are max distance apart. So let's look at vulnerable time from the max propagation delay from the frame bit from A to reach out to D, right? So at time T1, this guy senses it. He tries to transmit, right? And the frame bit has to travel, right? And it has to travel over time. So that's why we're putting it as a slanting line and not straight line. And so if B is trying to transmit at T1, right, he's not going to sense because the bit has not traveled. The signal has not propagated completely. The water has not flowed to the other end. And so the vulnerable time here is this time, right, which is your frame, the propagation delay that you have, where this time you could still have the collision happening. And that time is basically your maximum propagation time. After that, if you are sensing, if any device is trying to transmit after the signal is reached, right, the energy deduction will be proper. And so he could go on to abort and report the medium is busy and will not start up. But between this period, right, the vulnerable time where there could be possibility of collision, that's what we explained in this case here, right? So here is where CSMA will suffer, and people were trying to work out how we could further minimize this. And so now what we're going to look at here is we're going to look at how CSMA protocol types came in, where we brought in certain rules. Now, if I go on to have a device going on to finding out the medium is idle, what should the station do? So the answers came in where they started to ask two questions. What should I do if the medium is idle? And what should I do when the medium is busy? We have to start answering this. So stations which are having frame to send will first have to come up with a decision. Okay, now the medium is idle. Can I immediately transmit? If I immediately transmit, is there any probability of collision, right? So what schemes, what types, we could bring in. And similarly, if I find out the medium is busy, how long will I wait for the medium to be idle, right? So as soon as the medium becomes idle, can I transmit? Should I have to wait for a random amount of time as soon as the medium becomes idle? All these questions comes in, right? So what should I do when the medium is busy? Should I have to wait? How long should I have to wait? Should I have to wait till the medium becomes idle, right? If the medium is idle, can I immediately transmit? These kind of questions started coming. And so there were three different types of CSMA that came in. You could make a note of this. So one is called non-persistent CSMA scheme, right? The second one is called one persistent CSMA scheme. And the third one is called P persistent CSMA scheme. All these non, one, and P refers to the probability. Okay, so what do you mean by that? Now, if your medium is idle, right, is it certain that you could transmit with the probability of 1? As soon as the medium, you found out the medium is idle, is called one persistent. One certain, 100%. Once you find out the medium is idle, transmit. Right? Non-persistent is not certain, right? So you're going to have, so we look at all these schemes, one persistent, P persistent, and non-persistent, and understand the pros and cons of each of these design. So looking at the one persistent CSMA, one persistent, what we're trying to do here is, so this is over the time axis, where the persistence, now what do you mean by persistent? Persistent meaning you're checking persistently, right? So every device here is going to check the medium status, right? So if the medium is busy, if someone is talking, wait till they stop. As soon as they stop, you can capture the medium, right? So that sort of competition is what in one persistent we are trying to do. So in one persistent, what we're trying to do is any station that has frames to transmit will first listen to the medium, right? He will continuously keep sensing the medium, right? So if the medium is idle, he will transmit immediately. He will not wait at all. So the transmit immediately is what, right? You're certain that you will immediately transmit at the probability of 1. But if the medium is busy, what should I do, right? I will continuously, persistently keep listening the medium until the medium becomes idle. That's why it's called, persistent schemes, where if the medium is reported to be busy. Now here, if you look at the medium is busy, but that station which is sensing the medium has frames to transmit. So he wants to transmit immediately, right? But since the medium is busy, he's continuously sensing, persistently sensing till the medium becomes idle. As soon as the medium becomes idle, he goes on to transmit immediately with the probability of 1. So that is what is called one persistent. But can you now think, right? what do you think will be the problem in one persistent? Will it always be good? Right? Or is there any problem in it? Now, the point here is, okay, only when one device in a LAN is basically using the medium, right? Then there's not going to be any problem. But there are multiple devices that are trying to use the medium, right? So if the traffic on the LAN is high, which means multiple stations has frame to transmit, and everyone wants to capture the medium, they're hungry to use the medium, right? In that case, one persistent will suffer. You know why? Because all these devices are selfish. They want to transmit their frames. So if multiple devices are waiting to capture the medium, they find the medium to be busy, they persistently keep checking. As soon as the medium becomes idle, all will transmit at the probability of 1, and that will in turn, the vulnerable time that you have, there's going to be collisions happening, and so it will become a worse scenario. So this is the problem in one persistent, where if two or more stations are ready at the same time, the collision is guaranteed to happen. But you know that you are not giving any room for idleness here. You want to capture the resource as soon as it is available. So if it is a very light load on the LAN where only one station is waiting, there was already an ongoing transmission by say A, right? And B is waiting to send. So as soon as A completes, B captures, then you're not going to have any idle time. You immediately use the medium. In that case, 1% will behave good. But if two or more stations are waiting, right? And that is where you're going to have a worse performance. So one persistent, please understand the drawback. So we will try to overcome this drawback with another scheme called non-persistent. So any guess what you mean by non-persistent? Just make a guess. What could be the problem that one persistent had, which non-persistent CSMA is trying to address? Look at the picture below and try to make a guess. Right. So here you don't see continuously you're sensing the medium. That's the first point that you have to understand here. Okay. So if a station has frames to send, is going to sense the medium, right? If the medium is idle, they will transmit immediately. There is no doubt in it. Otherwise, if the medium is busy, unlike the previous case where you continuously sensing till the medium is becoming idle, here we are not going to do this. If a medium is busy, you will back off. Back off meaning what? You will go and wait for some random amount of time and then repeat one. So this random amount of time is going to further reduce the collision. So that is the idea here. So if a medium is busy, you wait, you back off and you wait for a random amount of time and again sense the medium. If the medium is still busy, you again wait for a random amount of time and then again sense the medium. So this random delay that you have, right, is further going to reduce the probability of collision. Even if two or more devices are trying to capture the medium, since the random amount of time that is being followed by each of these devices will only reduce the probability of collision, unlike the one persistent. But there is a problem when one non-persistent. Can you tell me what could be the problem? Just think now. So now we are reducing the probability of collision when there are multiple devices waiting to capture the medium, but the medium is busy. So you wait for a random amount of time before you start, sensing again, right? But here, look at this now. Since you are waiting for a random amount of time, now after this point, the medium has become idle, right? So there is a lot of idle time here before you start capturing this. So this random amount of time can lead you to wasting the resources because you're wasting the time where the resource could have been utilized. And so the bandwidth is wasted, right? If the waiting time is large enough where the medium becomes idle. And so this non-persistent could suffer from bandwidth wastage because of the idleness in the time, and that is due to the random amount of time. Unlike in the one persistence where lighter load, you immediately go on to capture the medium and don't have any idle times, non-persistence will have this issue of bandwidth being wasted because of the time idleness that could be there. But if it's a higher load, then non-persistent could be a very good scheme compared to one persistent, right? Where they are trying to reduce the probability of collision. So that is the trade-off that we have. So having understood one persistence pros and cons, and having understood non-persistent pros and cons, let us now try to club write the pros of non-persistent and one-persistent and come up with a scheme called P-persistent CSMA. Right? So the P-persistent, the P stands for the probability P here. So just imagine that you're going to follow something like one persistent CSMA, where if a station wants to transmit, they first listen the medium, right? But here you're going to continuously keep sensing if the medium is busy until the medium becomes idle. But as soon as the medium becomes idle, you're not transmitting with the probability of 1, but you're transmitting with the probability of P. Now, this is where we are trying to reduce the probability of collision. But at the same time, you also don't want the idleness to be brought in. And so what they are doing here is they're going to divide the time into time slots. Let the time slot duration be equal to your propagation delay. So what is the idea now here is, once you are going to persistently keep sensing the medium, if the medium is idle, you transmit with the probability of P, right? Or you wait one time slot with the probability of 1 minus P and again repeat this, right? So if the medium is busy, right, you're going to continuously listen until idle. But as soon as the medium becomes idle, you're not going to capture the medium with the probability of 1, but you're going to try to capture the medium, transmit with the probability of P and wait with the probability of 1 minus P for the next time slot and repeat 1. So here when the load on the traffic is high, multiple devices wants to capture the median. This will further reduce the probability of collision because you're transmitting in the time slot only with a certain probability. Right. So it's like you make a toss of a coin. If it comes head, you transmit. Otherwise, you wait for the next time slot and again repeat this process. Right. So in that sense, we could further reduce the probability of the collisions like non-persistent. Right. And I'm sorry, this is put reverse here. So the idle time is reduced like your non-persistent, which was there. Because you have a time slotted base of allowing the transmission, right, of the probability, right? And also, unlike the one persistent scheme where you had certain collisions when multiple devices are waiting to capture the medium, you could reduce the possibility of collisions here. So that was the idea. P persistent strategy came in. So this is a flow chart to explain this. In one persistence, you are in a loop where you're checking the medium if it's busy, and once it becomes idle, you transmit. Right? Otherwise, it's in the continuous loop. Whereas here, if the medium is busy, you wait randomly and then again check if it's idle, you transmit. If it's idle, you transmit, certain. Right? So, but yeah, the amount of waiting time being random here brings in wastage in your channel idle time. Right? Whereas here, multiple stations are trying to capture, then there is collision. So to bring in this, here we are trying to bring in a case where if the channel is busy, right? Once the channel becomes idle, you generate a random number and you go on to check whether it is with the probability less than or equal to probability, you transmit in that time slot. Otherwise, you wait for a time slot, right, and again repeat this process, right? So this is the way P persistent tries to do, where it brings in a probability to transmit in this time slot or wait for the next time slot and repeat the procedure. Okay, so I think with these three different types that you had, the first standard Ethernet basically went on to adopt one persistent scheme at the initial aspect of it, but they augmented with an approach called collision detection. Okay, why this came in? Because we are now looking at when you're transmitting, you want to reduce the probability of collision. That is what we are looking at. But what if collision happens? What next? Right? So here in CSMA CD, which was used in 802.3 standard Ethernet, right? They went on to augment and feature called collision detection. Right? If I detect collision, I should stop, right? I should not allow further transmission because it's already destroyed. So that mechanism to detect collision and then take the next set of action steps was done in CSMA CD. Okay, so in this method, what you're going to do is when you are trying to send a frame, right? You're going to parallelly keep monitoring that station which is sending the frame is going to parallelly keep monitoring the medium to see whether its transmission is successful or not. In case if there is a collision happening, another signal got collided or multiple devices got collided, then there's going to be an abnormal increase in the energy reduction process, right? And this like a spike. Okay, so that abnormal increase in your voltage spike levels that happens, then you can go on to stop and go on to resend it after running your BEB algorithm. If you remember, BEB algorithm is something that was used in Aloha, Slaughterland, all random access protocols started to use this binary exponential backoff algorithm, because when they wait for a random amount of time, they back off, right? And that random amount of time, BEB binary exponential backoff strategy was used. So we'll understand this mechanism in the flowchart, that comes in. Okay, so in CSMA, if you look at all the methods, right, the collision has occurred, everything is waste. Even if the first bit itself got collided, whatever you're transmitting after that is all damaged, right? So the frame as such is destroyed and the channel is unstable during that point. So you have to keep transmitting fully your frame, even though it is destroyed, right? So the mechanism that was brought in, why don't we do an early detection process? If when the collision is, you can have the mechanism detect that there's something abnormal happened, and you stop and further avoid transmitting the full frame, right? This mechanism was brought in, right? So what for that, you're going to do two processes at a time. You're not just going to transmit in a port, but you're also going to listen over the port, right? For an abnormal, energy detection process. So this, you could stop your transmission if the collision has occurred, and so you could further reduce the wastage of your channel, right? So that was used in your bus topology LANs, right? The standard Ethernet that was talking, CSMA CD is being used. I hope you are able to follow the mechanism that was brought in the collision detection process. So let's get on now with understand from space-time model, right? So that we could understand how CSMA CD, right, the mechanism of collision detection is being brought into these devices, that intelligence. So A, B, C, and D are the four stations that are tied over the bus. Now, all these schemes are applying, say, some persistent strategy that is there. Despite there, right, you're going to have collisions because of the vulnerable time that you have. So, suppose A has a frame to transmit. Now, at time T1, right, he senses the medium, finds the medium to be idle. He starts transmitting the first bit. Okay. Now, station C at time T2. T2 is greater than T1, but you know that it has not propagated. It is in the vulnerable time. So what happens? He goes on to sense the medium to be idle and he starts transmitting. Say, let's use one persistent. Okay. So now what happened? The first bit of A and first bit of C got collided at some point, right? And this collided signal, these guys are going to keep transmitting. When they are transmitting, right, they're also listening to that. And so this first bit of A, which is collided with the first bit of C, it takes some time to propagate, right? At time T3, C goes on to detect some abnormal energy detection. As soon as he detects that there's an abnormal energy detection, he detects that there's a collision and he aborts the transmission. He has not completed his frame transmission. This is the early detection process. So he sees that, okay, some signal is added up to the signal energy and he sees a spike. So you look at, to explain this, I think I'll show you the picture to understand the level of the signals here. So if it's a normal frame transmission, only one has captured the medium, you could see some voltage level, right? But in case if there is a signal getting added up and there is some kind of a signal spike happening, that's called the abnormal energy levels. Right? If there is no signal transmission, the medium is idle, then it's like a zero energy level. So these are the three states of the medium that we can take, and now we'll be bringing in an abnormal energy direction. That's what these stations are trying to do in these schemes. So station C is also going to monitor, station A is also going to monitor. Now station C at time 3 has detected it, then he stopped the transmission. Station A, for that bit collided signal to transmit and reach to him takes some time, T4, right? But during that time, he's still transmitting, right? So this will work only during, when you're simultaneously transmitting and listening, because after you're transmitting, you're not going to listen over the medium. Okay, so the simultaneous process of transmission and listening happens. And during this transmission process, when you are having a collision happening, then you go on to stop, abort the transmission, right? and then go on to retry after running your BEP algorithm, right? Because you can't retry immediately after you aborted it, right? So, so that is a mechanism that is brought in CSMA CD. But there are some challenges here. CSMA CD, if it has to work effectively, we'll have to look at what all are to be addressed here. So let's look at this. We will look at it from the space-time model, from a neat to the understanding. So here you look at the yellow part and the green part, yellow part and the blue part. So at time T1, station A starts to transmit its first bit. So the part of A frame is getting transmitted, simultaneously listening. Now station B at time T2 sends the medium to be idle, and he also started transmitting. Right, so the blue part that comes in, right? So he is going to transmit, but the signal has reached, and these two signals has collided, and the collided signal to reach, then come to him, right? So he at this T3 point, station C detects collision and aborts the transmission. So the part of C frame which is collided, right? At T4, this guy detects and he stops the collision. So both of them have aborted their transmissions as such. But please understand the transmission, he has to keep transmitting, right? If he has to detect for the propagated signal to come. So what should be my minimum frame size such a way that I could do effective collision detection? Because before my transmission is over, right, the collided signal comes later, then it's not going to be able to have this abnormal energy detection happening. So during the time, transmission listening happening in sync, and then you have to abort during your transmission time, you have to continuously keep transmitting, right? So what should be the minimum frame size that we need to adopt? This is the discussion that we have to work on. So there is a restriction in the frame size for your CSMA CD to work. So before sending the last bit of the frame, you should be in a position to detect if there is any collision or not, and then abort. Otherwise, you will not be able to detect. Okay, so we're not going to keep a copy of the frame, right? And we're not going to monitor the link after your transmitted. So that's the mechanism that is being brought in. So for that to work on, your frame transmission time, you can write down this. The station's adopting the frame transmission time, right? He's transmitting frame. You should keep transmitting at least twice the maximum propagation delay. So for the collision detection to work, the TFR, the frame transmission time, should be at least 2 times the maximum propagation time. Why is that? If you look at it, now let's understand this from the space-time model itself. You know that if you're transmitting the first bit, it has to go and reach the dead end, right? It takes TP. Say at this point collision happens, and that has to propagate and come back. You will take another TP time. So TP, 2 TP, round trip time. During this time, the collided signal, that comes back to you, right? It will take 2 TP, right? So you have to keep transmitting till that time to see that the spike happen. Okay, so that's the point here. So the frame transmission time should be at least greater than or equal to 2 TP. And so based on this, what should be your length of the frame? If you are transmitting at certain bit rate, right? So the standard Ethernet was operating at 10 Mbps. So this is the rate at which you're transmitting, right? You should now know what should be the length of the frame if you're using a standard Ethernet, right? Such a way that if you know what is the propagation delay, the max propagation delay that is offering, you will be able to come up with the design of your frame length, minimum frame size, so that you could go on to detect here, right? So the requirement is to keep transmitting after 2 TP, because the worst case is the effect of the collision will take another TP time. So the idea is this. So I think having understood this picture, how the space-time model we are using it to capture, and we'll have to now look at that from a problematic point of view. Right? What could be the minimum frame size if I'm adopting certain configuration settings? So let's go on and understand and apply this in a problem. Now look at this problem. You can make a note of this problem. There is a bus network which is using CSMA CD. Okay, and the bus, the bandwidth of the bus is basically 10 Mbps. So it could maximum support 10 Mbps speed. Okay, now given in your question, the maximum propagation time, the propagation delay is 25.6 microseconds. Can you find out what is the minimum size of the frame that the device have to transmit for CD to happen correctly, for CD to be effective, collision detection to be effective? Can you now work out? right? So what you've been given now, so you've been asked what is the length of the frame, minimum length of the frame for my collision detection to be effective. So I should keep transmitting, right, before the collided signal reaches to me, right? So in the worst case, even after 2 TP, right, you should be transmitting. So with TP is given to you, 2 TP is going to be what? 51.2 microseconds. So you should be transmitting at least 51.2 microseconds, right, for your collision detection. So you have to transmit for at least 51.2 microseconds. You could transmit at the rate of max 10 Mbps. So you know L by R is a bit rate at which you're transmitting, which is the max bandwidth that could offer, is going to be your frame transmission time. This formula you know. So now I've told you that TFR should be at least greater than or equal to 2 TP, which means it should be at least 51.2 microseconds. So what should be the length of the minimum size of the frame? L is equal to TFR into the rate at which you're transmitting. So you're transmitting for at least 51.2 microseconds at the rate of 10 Mbps. So if you go on to calculate this, this will come on to 512 bits. In other way, to represent it as bytes, it's going to be 64 bytes. So the standard Ethernet adopted this standard telling that, hey, for collision detection to be effective, the minimum size of the frame should be at least 64 bytes. Larger than that is fine. But for your collision detection to happen effectively, it should be at least 64 bytes. So that was the standard that was adopted, in terms of the minimum size that the schemes happen. And then later it all increased, and then there was a scheme where you don't need CSMA CD. So this is how it has evolved. But yeah, CD is a augmented procedure to detect collision. Okay, so what we could ideally do here is you can use any persistent scheme, right? Before you're transmitting, you want to ensure that you want to minimize collision is one thing, but collision if can happen because there's a vulnerable time. So when you're detecting the collision, you have to abort the transmission, right? For that abort to transmission to happen, you need to have a minimum frame size so that you could detect, right? And then once you've detected, there was another scheme that was also brought in. You can just make a note of this, but not really get bogged off. It is like sending a alert signal to everyone after you're aborted the transmission. Everyone has to know because everyone is receiving this, right? So you have to know that this is basically there's a collision happening. And so that alert signal is called as a jam signal. It's a 48-bit jam signal where the stations which have aborted the transmission will go on to transmit a jam signal to notify all the stations that they have to discard, right? That the frame that they have received, right? And so after sending the jam signal, all these sending stations will then run the BEB algorithm, will wait a random amount of time before they go on to retry the next attempt, right? So that is the point here that we are trying to bring in. So BEB is the scheme for the retry interval. And you know the advantage of the BEB algorithm. We want when your multiple stations are waiting to retry, the random amount of time that is waiting is based on the number of retry attempts, right? So when you're choosing a random number r between 0 to 2 power k minus 1, where k is the counter value, retry atoms value. So here, if you look at the flow chart, unlike the slotted Aloha scheme that we had, the counter begins at 0. Then the station is sensing the medium. He's applying one of the persistent method, whether 1%, p%, and non-persistent. Now, if the medium is idle, he goes on to transmit, right? So that is the ultimate thing here. Now, when your transmission is being done, you're also parallel listening to the medium. If there is a collision detected, right, then you have to abort the transmission, send an alert signal, jamming signal to make everyone aware of the collision, and then you have to retry. So you increment your counter value, you check if you have reached your maximum bound of K max, right, before you give up. But till that, you could go on to retry by choosing a random number value, which is from 0 to 2 power K minus 1. This is your binary backoff algorithm because you choose a random number, you multiply that random number into the propagation delay, you get your backoff time. So you wait for a random amount of time, you back off and you wait for a random amount of time before you again retry and apply your sensing and then trying to do this. So this is these all are similar. What is new here is this part, right? This is where the CSMA CD mechanism comes. Okay, I hope you've understood CSMA series. So there are multiple points that here is there, right from the minimum frame size for the collision to be effectively detected, right? And also the BEB algorithm that we are bringing in. So the BEB algorithm is something which is, that we are trying our best to basically reduce the collision in the further attempts, right? And that will give you the amount of time that you have to wait. The amount of time, again, we can call it in terms of, because we are saying it in terms of R into TP, right? TP, if you take it as a slot time, the number of slots that you're going to wait, right, is going to be a random number of slots. That depends on the value of K. Okay, so but yes, how long? What's going to be the maximum interval? Suppose you choose k is equal to 10 max before it, right? Then your interval will be from 0 to 1023, 2 power k minus 1, 2 power 10 minus 1. So these many number of slots you can wait, and so you minimize the probability of collision in your retry atom. So that is the idea behind exponential backoff, in specifically binary exponential backoff algorithm. But this again has drawbacks, right? All random access protocols were typically using for retry atoms exponential backoff algorithms, where it reduces the chance where two waiting stations picking up the same random amount of time is going to be reduced. That's what we are trying to do here. So when the network traffic on the LAN is basically light, right, it results in a minimum waiting time, right, before transmission. But if there's more traffic on the LAN, congestion is increased, then every stations are trying, right, and they have a larger amount of time to wait, right, and all this. This is going to be a problem, right? Here, what will happen is this algorithm will give in a last in first out effect. Some stations are waiting for a long time to capture the medium, and so their retry interval is larger. But suddenly, later point of time, a station which is coming fresh will capture first, right? So the last station which has come, which has come at the later point of time will be the first one to use it, because he's having a very shorter time to use the medium, unlike the one which is having a larger interval of time waiting, right? So this is called last in first out. This effect is there in exponential backoff algorithm, which I think this is going to be one of the drawbacks of your BEB approaches. Okay, I think we have come to a conclusion where we have understood CSMA CD. We will get on with CSMA CA and the control access in the next lecture, right? Thank you guys. Thank you for your attention.